know how good this analogy is going to be in kind of explaining to you the notion of heat storage. We are going to do another one where we pull out some lights and put out some rocks and put out some wood and have you guys kind of understand a little bit about something called thermal mass. Okay? Right now I'm just using this analogy to kind of give you guys a picture of heat energy being stored in something and then expended. So heat is always moving from hot to cold, right? So if we imagine that this represents cold, this jug of water represents this concept of cold, and this jug of water represents hot, right? The notion of thermal mass is the ability to receive a lot of heat energy, right, and store it. But it can't store it forever, right? As soon as the temperature drops, it starts to release some of the heat to the lower temperature, correct? So we can think of that possibly as a little hole in the bottom of the bucket. And so we take this water and pour it into this thing, and so now this thermal storage device has stored up a bunch of heat energy. But it's going to slowly leak out the bottom. And after a while, it's going to be completely empty. So later on that day, it might be to here, right? And the next day, it might be down to here, empty. Okay? The fact that it could hold all of that stuff meant that it had thermal mass, it had the ability to store heat energy. Remember, the heat energy is molecules vibrating, okay, in a solid substance. So some materials are good at storing energy. You've already covered that in the heat lecture, and other materials are not. What is a material that is not good at receiving heat energy? What? Going back maybe 3 classes ago? No, what's it called? What is a material that is not good at receiving or transferring heat energy called? It's an insulator, correct. And what is one that is really good at receiving or transmitting energy? What's that called? It's a conductor. You guys also learned that a conductor is not necessarily the same thing as ability to store it, right? So what I want you guys to understand about thermal mass is that what you're looking for in thermal mass is something that will conduct energy. It will conduct heat energy, but not real well. Because if we took a pound of copper and we heated it up to 150 degrees, it would very quickly cool back down. You need something that doesn't conduct really fast. But at the same time, you need something that will conduct. Okay? So if you guys remember that 1 cubic foot of water had 10 times the heat storage capacity of copper. And so there's this sort of interplay of density and insulative property and conductive property, right, that puts things on different scales. And what I want you guys to understand is that the notion of conductance is not the only factor involved in thermal mass. Okay? So, okay, how many minutes are we at? 4. So, okay, we're going to take and we're going to put a rock and a piece of wood out, and we're going to get a timer, and we are going to put a light on the rock, a heat lamp on the rock, and we're going to let it sit there for, 5 minutes. Then we're going to, and on both the rock and the piece of wood. All right? What's going to happen when you turn the heat lamp off, if you touch them, they're both going to be warm. Okay? More than likely, the wood will be warmer than the rock. But within a few minutes, the wood will be much colder than the rock, and 10 or 15 minutes later, the rock will still be warm. which of those two had better thermal mass, the wood or the rock? Rock. Okay? And so that's the thing that you guys got to understand, that thermal mass objects, things that are good thermal mass objects, don't have a super high conductance, but they have a lot of density. And a rock is like that. It is not a super high conductor like copper, right? But at the same time, it is a very dense substance. Okay? All right, so let's go ahead and stop that.